All right, so here we are back for the fourth segment in section 5.2. I've selected a couple of sort of relatively shorter proofs. I mean, in segment 3, we went through some that were a little more challenging. I've got some that are sort of quick layups that I'd like you to see just so we have a little bit more examples to work with. So I'll just switch over to the document camera and start going here. These are all going to be basically the same kind of setup where we are trying to prove that left-hand side equals right-hand side, something along those lines. So I believe we are now on page 10. Woo, it's a lot. Okay, so let's start with a couple of simple ones. Show and cotangent of x times cosine of x equal to cosecant of x minus sine of x. Sorry about that, I got a little sandwich there. Okay, so here, just a quick discussion, and then I'll move on. I think that if you're looking at these two, notice that they have trigonometric functions of approximately the same complexity. 2 over here, 2 over there. Remember I had said at one time, multiplication is more complicated than addition or subtraction. And so that's sort of my thinking is, maybe I ought to start with this left-hand side and see if I can't get it to look like the thing on the right-hand side. So that's how I'm going to start. I'll start with cotangent of x times cosine of x. The first step that I'm going to employ is to convert, just because I really don't know exactly how to get there, I'm going to convert this to cosine over sine. So we have cosine of x over sine of x times cosine of x. That is a quotient identity. And the next step, I'm going to go ahead and combine those together. So I have now cosine squared of x in the numerator over sine of x. This is where I'm going to start looking at the target. See how the target has 2 terms? Well, I don't have 2 terms. I've got this numerator that is a single term. It's a monomial. The denominator is a monomial. So maybe the one possibility, notice that this is a squared trig function. So there's the insight is, hey, anytime I see a squared trig function, maybe I should try using a Pythagorean identity to get myself out of this. So that's exactly what I'm going to do. I'm going to, cosine squared is actually the 1 minus sine squared. That's a Pythagorean identity. And now I can split this up into 2 terms. Notice I have 1 over sine of x minus sine squared of x over sine of x, right? See where we're getting here? This is just an algebraic step. I just separate the 2 terms. Notice that the left term is cosecant, which was the term that we wanted. And the second term, when you do some cancellation here, you have sine squared over sine. This is just going to be sine, which is the second term. That actually takes two different arguments, so I'm going to write it as such. So this is cosecant of x minus sine squared of x over sine of x. This is a reciprocal. And then finally, cosecant of x minus sine of x. And this is just an algebraic cancellation. Okay, so let's verify. We started with the left-hand side through a series of logical arguments, every one of which is justified. We end up with the right-hand side. So this proof is done. Okay, I'm going to do another real quick one here. This is, again, section 5.2, page number 11. Second example, let's prove that sine of x over cotangent of x is in fact equal to secant of x minus cosine of x. And similar to the last one, the argument here is the division is more complicated than subtraction. So I'm going to start with the left-hand side. I've got sine of x over cotangent of x. And just like with the last problem, I don't know how to work this other than just to maybe try to convert this into sines and cosines and see what pops out. This proof happens to be awfully similar to the last one. So I will take that first step. So sine of x over the ratio cosine of x divided by sine of x. Got to be careful with order of operation here. This is a quotient ID. Now from here, I'm going to simplify this complex fraction. We end up with sine squared of x over cosine of x. Hopefully this is starting to look familiar, but that's just an algebraic step. Again, just like with the previous problem, I've got two terms on my target. I've only got one term here, so maybe, again, we have a sine squared there. Maybe we can use a Pythagorean identity, and I think if you were paying attention, I think you already know where we're going with this. It is almost the same problem. This is a Pythagorean ID. We'll now separate these into two terms, one over cosine of x minus cosine squared of x divided by cosine of x. And just like we had before, this is an algebraic step. Just like before, here we have a reciprocal identity, gives us our first term that we were looking for. Secant of x, there's our secant of x. I'll do this in two steps so it's real clear what just happened. Cosine of x, this is a reciprocal identity. And the algebraic cancellation, we end up with secant of x minus cosine of x. And that is an algebraic step. So just to verify, we started with the left-hand side, a series of logical arguments, each one of which is justified. We end up with the target. Okay, so this proof is complete. Really quick. Of course, these will be on up on the blackboard here when I'm completed. Okay, let's try another one. Those both involve Pythagorean identities. Let's move to something that's maybe a little bit different. You may see something like this in the homework. Hard to say, but I'd like to just take this time to put as many different proofs in your hand as possible. And of course, there's hundreds of videos out there on the internet. So I'll try to focus on some of these. So example 3, let's prove that 1 over cosine squared of x plus 1 over sine squared of x is equal to the product cosecant squared of x times secant squared of x. Sorry, I got that a little bit sandwiched over. I probably should have spaced that a little bit better. Okay, so this brings up an interesting point. Notice prior it was like, well, we boiled something down to the point where we had one term and we were trying to turn it into two. Here, we might think that we can do the same thing, but it's not real clear which term to do. So I'm thinking that maybe because this has division involved and has fractions and an extra operation, that the left-hand side is probably more complicated. So that means I need to, at some point during the process of doing this proof, I have to take two terms and turn it into a single term. Okay, so let me kind of talk that through. So 1 over cosine squared of x plus 1 over sine squared of x. Now, if I'm trying to convert this and take two terms and convert them into one, I'm basically performing the operation. But these are fractions, and so the only way to add fractions is to get common denominators, right? So I'm going to basically multiply this by sine squared over sine squared, this term by cosine squared over cosine squared. Then we'll have a common denominator, and we can add it. I'm not going to show every single step to that, but basically you're going to end up with sine squared of x over cosine squared x times sine squared of x plus cosine squared of x. I'm just going to do this because they're in space. Same. Right? That's the least common denominator coming in there. So performing this, and that is a purely algebraic step. Performing this operation, then I have sine squared of x plus cosine squared of x all over the least common denominator, which is cosine squared of x times sine squared of x, right? And now, and again, we're still just doing a bunch of algebra. Staring you right in the face is the first Pythagorean identity in numerator. Right? So this actually becomes 1. So we have 1 over cosine squared of x times sine squared of x. This is a Pythagorean ID. And this is looking very, very similar to where we were at, where we wanted to get to, right? We just have to do a little bit of manipulation. I'm going to actually break this into 2 products. So this is 1 over cosine squared of x times 1 over sine squared of x. Again, this is a purely algebraic step. And then, of course, okay, so 1 over cosine squared, well, that's secant squared. 1 over sine squared, well, that's cosecant squared. So I end up with secant squared of x times cosecant squared of x. This is 2 applications of reciprocal identity, 2 different reciprocal identities. Notice, aside from commutativity, that's what we have on the right. So I guess technically there is one more step. Cosecant squared of x times secant squared of x. This is a purely algebraic step. So we started on the left through a series of logical arguments, each one justified, and we end up with the thing on the right. So this proof is done. Okay. Next, I think I'm probably only going to do maybe 1 or 2 more, and then this will probably, aside from one other topic, this will be it for 5.2. So section page now 13. We want to show, this is number 4, I guess, show that, which one did I want to do? Okay, 1 minus cosine of x over 1 plus cosine of x is equal to the perfect square cosecant of x minus cotangent of x quantity squared. Now this is a situation where both sides look relatively complex. But I'm going to make the assumption, believe it or not, that this is the side I probably want to start with. And the reason being is that I can bust this down into sines and cosines, maybe distribute that, and then see what falls out. And I think I'm probably going to be pleasantly surprised. So that's actually my strategy, is to actually start with the right. So cosecant squared of x minus cotangent, or sorry, it's not squared. Cosecant of x minus cotangent of x quantity squared. Okay, so let's distribute this. We're going to end up with cosecant squared of x minus 2 cosecant of x cotangent of x plus cotangent squared of x. Okay? Now, each one of these terms can be, by using a reciprocal or a quotient identity, we can get those all in sines and cosines. So the next step would be 1 over sine squared of x minus 2 times, let's see, so that's 1 over sine of x times cosine of x over sine of x plus cosine squared of x over sine squared of x. And notice every one of these terms has a sine squared in the denominator. Now, I kind of run out of space here, but this is both r and q. It's my rationale for this. Okay? So I can combine all these terms, I could have maybe done this a little bit different way, but so be it. So now since they all have the same denominator, I can add all these fractions together. I end up with 1 minus 2 cosine of x plus cosine squared of x in the numerator, and in the denominator, I have sine squared of x. This is just an algebraic step. So maybe now, because look at what the target is. The target has a 1 plus cosine in the denominator and 1 minus cosine in the numerator. I can probably get you notice this is a perfect square right here. This can be factored. You need to do something with that denominator because it still has the long trig function. So maybe the next step would be to get rid of the sign by using the first Pythagorean identity. So I have 1 minus 2 cosine of x plus cosine squared of x. Nothing changes in the numerator. And in the denominator, I get 1 minus cosine squared of x. This is just a Pythagorean ID. Okay. Now notice, as I was alluding to before, both the numerator and the denominator can be factored. This is going to be a perfect square, and this is a difference of squares. So let's go ahead and do that factorization. I have 1 minus cosine of x squared all over 1 plus cosine of x times 1 minus cosine of x. Okay? And that's just a purely algebraic process. Now notice, I can kill off one factor of 1 minus cosine of x by canceling it with the one that's in the denominator, same term, and what I'm left with is 1 minus cosine of x over 1 plus cosine of x, which happens to be what we wanted. Now notice, in this case, we went from the right to the left. Started with the right, a little bit messy in there. We did a series of arguments, and end with the thing on the left. So this proof is done. Okay. I'm gonna do one more proof, and then I'm going to talk a little bit about this. If you want to show that something's not an identity, I think it's in the text, and in the interest of time, I may actually ignore that. Okay, so I believe this is the 5th example. So we would like to show that sine to the 4th power of x minus cosine to the 4th power of x over sine squared of x is equal to 2 minus cosecant squared of x. Wow, that's kind of weird. But it's going to work out just fine. Okay, so I'm going to make the argument here that the left-hand side is the more complicated side. There's a lot more going on there, even though the thing on the right-hand side has a trig function that maybe isn't as comfortable. So I will start with the left-hand side. And I want you to notice that the numerator is actually a difference of squares, right? And we don't really have much to do with the denominator yet. But I think the first step I'm going to do is I'm going to factor this. And I end up with, well, this is basically a squared minus b squared, right? Where a is actually sine squared and b is cosine squared. So this ends up being sine squared of x plus cosine squared of x times, I'm kind of running out of space here, sine squared of x minus cosine squared of x all over sine squared of x. Now notice that term is the first Pythagorean identity, which means it disappears, right? It becomes 1. So what we're left with is, and by the way, this is just an algebraic step here. What we have is 1 times the quantity sine squared of x x minus cosine squared of x all over sine squared of x. Okay, the one is unnecessary, but this is a Pythagorean identity. Next, notice that the target has two terms. And so it might make sense to try to break this up into two terms. So we end up with the first term is sine squared of x over sine squared of x minus cosine squared of x over sine squared of x. So we're getting close. I mean, we're kind of circling the drain here a little bit, but this is just an algebraic step. Because notice, this is going to be 1, and that's going to be cotangent squared. Right? But that's not our target, so maybe if we, I mean, that's the pretty clear, obvious relationship here. Let's just go ahead and do that. I have 1 minus cotangent squared of x, and this is actually algebra and a quotient identity. Okay, I'm starting to sandwich things together a little bit. Now, here's the thing to observe. The target has a cosecant squared in it. We now have a cotangent squared. And so let's use the third Pythagorean identity to convert cotangent to some version that involves cosecant. That's the thinking here. So this is going to be 1 minus, and remember, cotangent squared is actually cosecant squared minus 1. So I'm going to put that in parentheses just so I don't mess up the signs, right? This is a Pythagorean identity. And now distribute, negative, negative, you're going to end up with 1 minus cosecant squared of x plus 1. That's just an algebraic step. And of course, this will combine as 2 minus cosecant squared of x, as was desired. So let's carefully look. We start with the left-hand side, and then through a series of logical arguments, we end up with the right-hand side. So this proof is done. Okay, I think I'm getting a little long on time, so I'm going to finish this video. And since the last piece of information is not something I'm terribly excited about, it involves showing that an equation is not an identity, I think it's sufficient to just look through the text, read the material on that. If there are some problems, it's easy enough to do. Basically, when you're trying to show that something is not an identity, it is in the vernacular of mathematicians, it's you're finding a counterexample. So in order to prove that something is not true, all you have to do is show that it doesn't work for some specific value. So that's the technique, and I don't think it merits an entire video to do that, so I'm just going to leave it at that. Okay, I will start recording section 5.3 shortly, and I will open up 5.2 for your entertainment. All right, thank you.